right. So this morning we are Is it clear?
No, it isn't.
It's not clear.
No, sir.
How about now? How about now? Can we see? Okay. So this morning we are looking at something called linear momentum and something related to linear momentum, which is called impulse. So without any delays, what our objectives in this case is to define and see what linear momentum is. So basically, linear momentum is something when we connect the mass and the velocity of an object, something we get when we multiply the mass of an object times the velocity of that particular object. So velocity is the speed of an object in a specific direction, and the mass of an object is the measure of an object's inertia. So when we multiply the mass times the velocity, basically what we get is called linear momentum. Okay. Then with this definition of linear momentum, we are also going to look at force. So far our view of force has been in terms of Newton's second law of motion. So we're going to start from Newton's second law of motion and try to look at force in terms of linear momentum. So we're going to see that when you look at force in terms of linear momentum, we actually come up with a very, very nice definition of force as how fast the linear momentum of an object is changing. Then using this definition of force which you're going to come up with, we're going to define a quantity which is called impulse of a force. The impulse of a force is basically what is known as the change in linear momentum. So we'll see what that is and how we get it. Then from that time onwards, we're going to also look at another important relationship, which is the relationship between linear momentum and kinetic energy. How is linear momentum related to kinetic energy? So we're going to see that. So to start with, we denote linear momentum with the symbol P, and linear momentum tells us about an object which is in motion. What does it tell us about an object in motion? It tells about the mass of the object. It also tells us about the velocity of the object. So it is basically a measure of the motion of an object. Previously, we have looked at motion, but when we looked at acceleration, we looked at displacement, we looked at these things, velocity and stuff like that, we were not interested in the mass of the object. We were never at any point interested in what the mass of this particular object is. However, you are going to agree with me that the mass of an object is very, very important when you're talking about motion of an object. So in this case, linear momentum is a measure of the motion of an object. Okay, how do you define motion in terms of linear momentum? And how do we define this linear momentum? Well, linear momentum is just what we get when we multiply the mass of an object times its velocity. Whether that velocity is the initial velocity or the final velocity doesn't really matter, but it's just the mass of an object times the velocity. So that's what you have here. So when we have the mass of an object, then this object has got a certain value of velocity. Then we multiply these, you get linear momentum. Now, how do we know that linear momentum actually gives us a measure of motion? Well, you can look at an example where the velocity of an object is equal to 0. In this case, this particular object is not moving. So if the velocity of an object is equal to 0, this velocity, which is 0, you multiply it by the mass of an object, you're going to get a linear momentum which is equal to 0. So in this case, when you have a linear momentum which is equal to 0, it tells you that the object is not moving. So as the velocity of the object increases, so you multiply the velocity times the mass of an object, then the value of linear momentum begins to increase. The mass of the object itself during this motion is the same. Okay, but as the velocity increases, then the linear momentum also begins to increase. So you are looking at an object in terms of its mass. You're also looking at an object in terms of its velocity. So basically, this physical quantity called linear momentum is what we use to measure how much motion an object is undergoing. We're looking at the mass of the object. We are also looking at the velocity of this particular object. So as I've said, the symbol for linear momentum is P. So here, this is a formula how we get linear momentum. P is equals to the mass of the object multiplied by the velocity. The other thing I want to bring to your attention is, of course, the SI units. So the units of linear momentum, mass is measured in kgs here. So you're multiplying something which is measured in kgs times velocity, which is measured in meters per second. So the units of linear momentum are kgs meters per second. The one thing I want to bring to your attention is, what kind of physical quantity is linear momentum? Is it a scalar or a vector? So what we have here, as you can see, we have mass, which is a scalar, multiplied by velocity, which is a vector. So when you multiply a scalar quantity times a vector quantity, what you get is a vector. So linear momentum is a vector. So when you're talking about linear momentum as a vector, it means that the direction of the linear momentum is very, very important. The direction of the linear momentum is very, very important. Apart from the direction, it also means that you might have to find a component of this linear momentum. You might be interested in what is the linear momentum along a particular direction. For example, along the x-axis or along the y-axis. So those are things you might be interested in. Okay. So that's basically what linear momentum is. Linear momentum is a measure of the motion of an object. And for us to have a very good, complete description of the motion of an object, we are looking at the mass of this object. We are also looking at the velocity of this particular object. So, and that's what we end up having here. P is equals to mv. So this is how we define linear momentum. Any questions so far on what we mean by linear momentum? Are we clear?
Yes.
Okay. The next thing we're going to look at is the connection between linear, how is linear momentum related to Newton's second law of motion? Now we know that Newton's second law of motion tells us what's going to happen. Newton's second law of motion tells us what's going to happen if you have something called the resultant force. If a resultant force, it says that if the resultant force acting on an object of mass m is not equals to 0, then there is going to be an acceleration. The acceleration which is going to be produced is going to be in the same direction as the force, but the acceleration is also going to be inversely proportional to the mass, and that's how we end up with this equation here. F is equals to ma. So the F here is the resultant force, and the m is the mass of the object. Then the a is the acceleration which the particular object is going to undergo as a result of the presence of this resultant force F. So you only have an acceleration when you have this resultant force or net force present. If there is no net force or external force present or resultant force, then a particular the object you're looking at, which has got mass m, cannot undergo an acceleration. And what do we mean by acceleration? Acceleration simply means that the velocity of this particular object is going to change. So whether the velocity increases or the velocity reduces, it doesn't really matter. As long as the velocity has changed over a short period of time, then that particular object has accelerated. Okay. So this is what we are told. This is what we know from Newton's second law of motion, that the force or the resultant force is equal to the mass of the object multiplied by the acceleration. However, we also know from our studies of what acceleration is, that acceleration basically is how fast the velocity of an object is changing over a certain period of time. So in this case, when you're talking about acceleration, and what we are interested in here is average acceleration. When it talks about average acceleration, our interest is only in the final velocity and the initial velocity. So the difference between the final velocity and the initial velocity, this gives us what we call the change in velocity, and this change in velocity divided by the time that gives us acceleration. So we have a very good formula or expression for acceleration. So we're going to get this acceleration formula, we're going to substitute it here. So when you do that, we end up having resultant force being equals to the mass, then the acceleration, which is v minus u divided by t. So we multiply this v minus times u, we multiply the u times m, we end up having mv, which is the mass times the final velocity, minus mu, which is the mass times the initial velocity, and divided by the time. This bit, mass times velocity is what we have said is momentum. This mass times velocity is what you have called linear momentum. So what we have here is the mass times the final velocity. So this bit is what we call the final linear momentum. Then this one here is the mass times the initial velocity. So this is what we call the initial linear momentum. So we end up having PF here, which is the final linear momentum, minus PI, which is the initial linear momentum. So this PF minus PI, if you work out the final, you subtract the final linear momentum minus the initial linear momentum, what you get is what is called the change in linear momentum. So this change in linear momentum is being divided by t. So you can see from this formula which you have come up with here that the force or the resultant force is equals to the change in linear momentum divided by the time. So basically this formula is telling you that force is a measure of how fast the linear momentum is changing with time, or the rate of change of linear momentum. That's what force is. Are we clear? It is like the way we defined acceleration. Say acceleration is how fast the velocity of an object is changing with time. In this case, we are defining force as how fast the linear momentum of an object is changing. Are we clear?
Yes, sir.
Yes. So basically, this is how force is defined in terms of linear momentum. How fast. So if you see an object of mass m, then this object undergoes a change in velocity. It means that the linear momentum of that particular object has changed. The change in linear momentum divided by the times across which this change in linear momentum is happening gives you the force which is causing that particular object to change its velocity. Remember what force is. Force causes the motion of an object to change. From Newton's first law of motion, an object at rest will remain at rest, or an object moving with constant velocity will continue to move with constant velocity until it is acted upon by an external force. The force is the changer of motion. So in this case, as you can see, when an object undergoes a change in motion, that change in motion, how much change has happened in the motion of the object, divided by the time through which this particular change happens, that is what you're calling the force. Okay. Next, there is another physical quantity which is related to what we have, what linear momentum, and that is what is called impulse. So impulse, basically, in a nutshell, impulse is a product of the external force or the resultant force which is causing the change in linear momentum multiplied by the time this force is acting on the body. So you have force, you get the force, then you multiply this force by the time the force is present. What you're going to get is something called impulse. And how do we do this? So basically the definition of impulse is based on this formula which you have here. So in that case, what we do is we simply make this bit delta P, which is the change in linear momentum, the subject of the formula. So we start with the force, the external force or the resultant force is equals to the change in linear momentum divided by the time. So we multiply by time on both sides. So if you multiply this side by time, you multiply that side by time, we end up with this. You end up with Ft is equals to the change in linear momentum. So this change in linear momentum delta P, which is equals to the force, the external force present, multiplied by this is what we're calling the impulse. This is what impulse is. Ft, the external force multiplied by the time. This is what is called impulse. This impulse is equals to the change in linear momentum. So this quantity we're calling delta P, the change in linear momentum. This change in linear momentum is what we call impulse. The change in linear momentum is equals to the force which is present, which is causing the velocity of the object to change, multiplied by the time period over which that force is present. We know that the change in linear momentum is equals to the mass times velocity, mv, final linear momentum minus initial linear momentum, which is equals to this. From this side, if you look at things from this side, where the resultant force is measured in newtons and the time is measured in seconds, then you can see that impulse has got units of newtons per second, newtons times seconds. Okay, so usually it's very, very important that you're able to, most problems, physics problems involve impulse.
Excuse me, sir.
Yes.
We explain on how the formula of impulse is coming out.
It's coming from here. F is equals to the change in linear momentum divided by the time. So we just multiply on both sides by t. When you multiply on both sides by t, this t at the bottom is going to cancel out, but there will be a t this side. So you end up having this. You're making this the subject of the formula. When you make the subject of the formula, delta P the subject of the formula, this is what you end up with, which is this. This delta P, change in linear momentum, is what is called impulse. Are we clear?
Yes.
Yeah. So the impulse is equals to the resultant force, or the force which causes acceleration, multiplied by multiplied by the time. Okay. So next example. So we've got an example of how we could use this. Example number 1. A 2 kg block is moving at a speed of 6 meters per second. How large a force F is needed to stop the brick in 7 times 10 to the power minus 4 seconds. So what we have here is the mass of the brick. The mass of the brick is 2 kg. Then we are told that it was moving at 6 meters per second. So this was the initial velocity of the block. Then it stopped. It comes to a stop. Needed to stop. So the final velocity of this block is going to be 0 meters per second, and the amount of time this block comes to a stop in is 7 times 10 to the power minus 4. So you can see from 6 meters per second to 0 meters per second, during this time, this is when this acceleration is happening. And when an acceleration is happening, it means that there is a resultant force which is present. When the velocity of an object is changing, whether the object velocity is increasing, or in this case the velocity is reducing from 6 meters per second to 0 meters per second, during this time when this thing is happening, there is a force responsible for causing this change in velocity, and that force is what is called the resultant force. So in this case, we know how much time it's going to take to come to a stop, so we have everything we need. So you can work out the impulse. So we know that impulse is equals to the change in linear momentum, and of course impulse is this, delta P. So we end up having delta P is equals to the mass of the object times the final velocity minus the mass of the object times the initial velocity. We know the final velocity. The object comes to a stop, so the final velocity is 0 meters per second. The initial velocity is 6 meters per second, and the mass of the object is 2 kg. So we end up having, we can work out the impulse. Delta P is equals to 2 kg times 0 meters per second minus 2 kg times 6 meters per second. So we end up having the impulse, delta P, being equals to minus 12 kg meters per second. So this is what the impulse is, the change in momentum. Okay. Now we also know that impulse is also equals to this, the force which is causing the acceleration multiplied by the time the force is present for. This is equals to the change in linear momentum. So what we have ourselves here is the change in linear momentum, which is minus 12 kg meters per second, like that. And we have been given the time this force is going to be present for, which is 7 times 10 to the power minus 4 seconds. So we can put that information together here. So we end up having Ft equals to minus 12 kgs meters per second. And we know how much time the force is going to be present for. It's going to be F times the time, which is equals to minus 12 kgs meters per second. So if you divide both sides by 7 times 10 to the power 4 meters per second, when you do that, you end up having force equals to minus 12 kg meters per second, then 7 times 10 to the power minus 4 seconds. So this gives you a force which is equals to minus 17,143 kgs meters per second squared, and this is approximately equals to minus 1.7 times 10 to the 4 newtons, and that's what you have as minus 17 kilonewtons. So approximately minus 17 kilonewtons. So this is how much force you need. Now if you look at this force which you need, you can see that this force is negative. This force is negative because this force is pointing in a direction which is opposite to the direction in which your object is moving. So your object is moving in one direction, this force is pointing in the other direction. We have seen that this kind of force which opposes the motion, which has got a tendency to bring things to a stop, this is what we refer to as the friction force. So in fact, the force we're looking for in this case is friction. So when something comes to a stop, this particular object coming to a stop loses its motion. So the change in momentum is negative, as we have seen, because the final velocity is 0, the initial velocity is not equals to 0, so the change in momentum is going to be equals to 0. And from that, we can work out, we also know that we can get the impulse by multiplying the force times the time, like this, and this is what we end up with. Are we clear?
Yes, sir.
Okay. Another example, example 2. A 15-gram bullet moving at 300 meters per second passes through a thick 2 centimeter thick sheet of foam plastic and emerges with a speed of 90 meters per second. What average force impedes its motion through the plastic? Okay. So again here we have a bullet which has got a mass of 15 grams, so we need to change that mass into kgs. And we see something happen here. The velocity of the bullet before it passes through the plastic is 300 meters per second, and the velocity of the bullet after it passes through the plastic is 90 meters per second. So you can see that the velocity of the bullet has reduced. So basically our bullet accelerated as it was passing through the plastic. It reduced in speed. And of course the plastic has got a thickness of 2 centimeters, like that. So as you can see here, there is a change in momentum because the bullet's mass did not change, but the velocity of the bullet changed. So there's a change in momentum. If there's a change in momentum, we can find out what the impulse is. Once we find out what the impulse is, it becomes possible for us to find out what force is impeding the object. But in this case, the difference is, unlike in example 1, in example 1 we were given how much time it took the object to come to a stop. In this case we are not given the time. What we are given is the thickness of the sheet through which the bullet passes through. So before it passes through the sheet, the velocity is 300 meters per second, that is the initial velocity. After it passes through the sheet, the velocity is 90 meters per second, which is the final velocity, and the thickness or the distance the bullet travels through the sheet is 2 centimeters. So using this information, we can find the acceleration. Then from that acceleration, we can find the time. Then we can find the force. And that's what we're going to do. So we'll start with, first of all, working out what the impulse is. The impulse is just a change in linear momentum. And that's what you have here. The change in linear momentum, delta P, is going to be the mass multiplied by the final velocity minus the mass multiplied by the initial velocity. The mass of the bullet is 15 grams, but you don't do your calculation in grams, you have to do your calculations in kgs. So you change your 15 grams into kgs, that's what you have there. Then the final velocity of the bullet on the other side when it comes out is 90 meters per second, and the initial velocity is 300. So the impulse is going to be 0.015 kgs times 90 meters per second minus 0.015 kgs times 300 meters per second, like this. So the impulse in this case is going to be equals to minus 3.15 kgs meters per second. So the change in momentum here is negative. This is telling you that this bullet has lost motion. Okay, the amount of motion the bullet was undergoing has reduced. That's what you get from the negative change in linear momentum. From this change in momentum, which is the impulse, delta P equals to minus 3.15 kgs meters per second, we know that also impulse is equals to this much. The force which is causing the reduction in velocity, which is the F, resultant force, multiplied by how much time it takes the bullet to pass through the plastic, is equals to the change in momentum, delta P. But we have this delta P. So this force times the time is equals to minus 3.14 kgs meters per second. In this case, we do not know what the force is. We are looking for the force. But we also do not know how much time it takes the bullet to pass through the plastic. So there are two things we don't know here. There is the force, which we don't know, which is causing the acceleration, but there is also the time it takes the bullet to pass through the plastic. However, there are certain things we know. We know that the plastic has got a thickness of 2 centimeters, which is 0.02 meters. And we also know the initial velocity of the bullet before it enters the plastic, which was 300 meters per second. And we know the final velocity of the bullet, which is 90 meters per second. So using this information, we can use this equation to find the acceleration of the bullet. V squared is equal to U squared plus 2AS. Our V is 90, our U is 300, our S is 0.02 meters here. V is 90 meters per second, U is 300 meters per second, our S is 0.02 meters. So we can substitute these values in this expression so that we can find the acceleration. From the acceleration, we know the formula for acceleration. We can use that formula to find the time. So that's going to be 90 meters per second squared, 90 meters per second, the whole thing squared, 300 meters per second, the whole thing squared, plus 2a, 0.02, the whole thing like that. Then you end up having this, like that, this, and that. So when you drop your units, you end up having 8,100 equals to 90,000 plus 0.04a. This 90,000, you take it to the other side, you end up having 8,100 minus 90,000 equals to 0.04a. This bit here is going to be your minus 81,900, and the other side you've got 0.04a. So you divide both sides by 0.04a, you end up having a is equals to minus 81,900 divided by 0.04a. So you end up having an acceleration a, which is equals to minus 2,047,500 meters per second squared. So this is going to be your acceleration. You can see that the acceleration is negative. This negative acceleration is telling you that the velocity of the bullet as it is passing through the plastic reduces. That's what negative acceleration tells you. Then you can look at the size of the acceleration. It's 2,047,500 meters per second. This is a very, very large value of acceleration. So this is telling you that the acceleration of the bullet reduces very, very fast. That's what it's telling you, that the acceleration of the bullet reduces very, very fast within this small distance of 2 centimeters, the thickness of the plastic. So this is the acceleration. Now we know the acceleration. With this acceleration, we know that acceleration a is given by the final velocity minus the initial velocity divided by the time. So we make the time the subject. When we make the time the subject of the formula, we end up having time t, which is one of the things we need to work out impulse, t is going to be equal to the final velocity minus the initial velocity divided by the acceleration. So we have the acceleration. With this acceleration we have found, it's now possible for us to find out what the time is. So that's going to be 90 meters per second minus 300 meters per second divided by this acceleration, and we end up having a time t which is equal to 1.03 times 10 to the power minus 4 seconds. So you can see that this object, the bullet, passes the time it's going to take the bullet to pass through the plastic is going to be very, very small. This is a very small duration of time. So with this time now that you've got time, now it becomes possible for us to find the force, because we're going to substitute our value of time here and we're looking for the force. So when you substitute our value of time here and we know what the change in momentum, the impulse is on the other side, so that's going to be the force multiplied by this amount of time which it takes the bullet to pass through the plastic, equals to this. So with that you divide both sides by this amount of time, so you end up having force F being equals to minus 3.15 kg meters per second divided by 1.03 times 10 to the minus 4 seconds. You end up having a force equals to minus 3.1 times 10 to the power 4, and this is going to give you a force which is equal to negative 31 kilonewtons. Again, our force, as you can see, is negative, telling you that this is telling you that as the bullet is passing through the plastic, it's not a smooth sailing thing. The bullet is being opposed. The motion of the bullet through the plastic is being opposed by friction. So there is friction as the bullet is passing through the plastic, and this is the size of the friction which is present. Any questions? So whenever bullet pass through things,
Sir,
yes.
so can momentum be lost to friction?
Can what?
Momentum be lost to friction.
This is what this thing is showing. This. Have you seen this? This is what it's showing. It's negative. The motion of the object is being lost, and momentum is a measure of the motion of the object. So this is telling you how much motion has been lost. And what's causing this loss of motion is a friction force. Friction always causes things to come to a stop. So things lose their momentum because of friction. So yes, that's what friction does. Are we clear?
Yes, sir.
Okay. Another example here, example 3. During a soccer game, a ball of mass 0.42 kg, which is initially at rest, is kicked by one of the players. The ball moves off with a speed of 26 meters per second. Given that the impact lasts for 8 milliseconds, what is the average force exerted on the ball? So here you have a ball which has got this mass. This ball was just sitting there. Then someone who is a football player decides to kick this ball. So when they kick this ball, we all know, I think people have kicked a ball before, that when you kick a ball, unless you're kicking a stone, that ball is going to move with a certain amount of velocity. So it moves off with a certain amount of velocity. So by doing that, this ball which has got a certain mass was at rest, then you've kicked it, it goes off with a certain velocity, you have changed the momentum of the ball. So we can work out what the change in momentum is. Then we are told that the impact of the kick lasts a certain amount of time, so we can find out how much force you exerted on the ball. So we know the mass of the ball is this much, 0.42 kgs. The initial velocity of the ball was at rest, is 0 meters per second, and the final velocity after the ball has been kicked is 26 meters per second. So immediately after the ball is kicked, this is the velocity of the ball. So we can find out what the change in momentum is. The change in momentum, delta P, is going to be equal to the mass times the final velocity. This is supposed to be minus here. The mass times the initial velocity. So this is supposed to be a minus sign here. So this is going to be delta P the mass of the ball times the final velocity minus the mass of the ball times the initial velocity, and we end up having a change in momentum which is equal to 11.05 kg meters per second. So you can see in this case the change in momentum is positive. It means that the ball has gained momentum. The motion of the ball has increased. Okay, we also know that the impulse in this case, delta p, is given by F multiplied by t. This is equal to delta p. So we know how much delta p is, how much momentum has been gained, and we know that the ball is kicked for a time period of 8 milliseconds, which is this much amount of time. So when you substitute that amount of time there, we end up having F, which is the force multiplied by the time, equals to this. So you divide both sides by the amount of time, so you end up having a force F equals to 11.05 kg meters per second divided by the time. You end up having a force which is equals to 1381. So basically this is approximately equals to a force of 1.4 kilonewtons. So this is how much force was exerted on the ball. Are we clear? So we have seen two cases. We have seen cases where the impulse is reducing, momentum is being lost, and usually the culprit when momentum is being lost is friction. And you have also seen another case here where momentum is gained, or when the momentum of the ball increases, and for you to increase the momentum of something, you need to exert a force. In this example, it is very clear that if you want to change the momentum of a ball, you need to kick it. And when you're kicking the ball, what you're doing is, for a very short amount of time, you exert a force. So depending on how powerful that force is, yeah, we all know what happens. Okay, any questions on this one? Are we clear? On what's going on here? Is it clear? Okay.
Yes, sir.
All right. Last but not least, in our lecture, we're going to look at the connection between linear momentum and kinetic energy. Now, we know that linear momentum is a measure of the object's motion. This is how we measure how an object, what the motion of the object is. But there's also another form of energy associated with motion. If an object is moving, there is a form of energy which it has, and that is what is called the kinetic energy. So let us see if we can connect these two physical quantities together. So we are going to start with linear momentum, which is P is equals to mv. So we square on both sides, so we end up having P squared is equals to mv. Since we have squared this side, we also square this side, so mv squared. So that mv squared is going to give us P squared is equals to m squared v squared. So next thing we do, so when you're doing, we square on both sides, you have not really changed anything. The next thing we do is we divide on both sides by m. So I divide this side, this m squared v squared, I divide it by m. Then this p squared I also divided by m. So when I do that, this m and one of these m's go. So I end up having p squared divided by m equals to m v squared. Then next I multiply both sides by half. So when I multiply this side, half times p squared over m, this is going to be also equals to be half mv squared. Now when you look at this side, half mv squared, this side half mv squared is actually what you call kinetic energy. This side half mv squared, this is what we call the kinetic energy of an object. So what we actually see is that the kinetic energy, which is given by half mv squared, is also equals to p squared divided by 2m. So you can express the kinetic energy of an object in terms of the linear momentum of an object. Here, p squared divided by 2m. Are we clear? Are we clear?
Yes, sir.
Okay, any questions? We have come to the end of our class. Are there any questions on what we have looked at? Yes.
Can momentum be zero, or maybe it's
Yes. Momentum can be zero. Remember what momentum is, right? Momentum is mass times velocity. So if the velocity is equals to zero, then momentum is zero. So right now, where you're seated, your velocity is equals to zero. So right now, you don't have any momentum. You're not moving. Remember what momentum is. It is a measure of an object's motion. So if your linear momentum is equals to zero, it simply means that physically you're not moving. You're just at rest. So yes, your linear momentum can be equals to zero. Any other question?
so sad as in momentum, though you are explaining it. Does
Yes.
it involve the whole object moving, or maybe just even part of it? For example, my arm and sort of that, or maybe the whole object has to move for momentum to be there.
We're talking about moving in a straight line. Remember, there's velocity, right? So if you're moving your arm,
Yes, sir.
how much distance have you covered in moving your arm?
Okay.
Yeah, you haven't covered any distance. There's another kind of momentum which is associated with things which are rotating and stuff like that. Maybe that's where your arm could come in. That is what is called angular momentum, but you're going to look at that later on, but not today.
Oh,
Yes.
okay, sir.
Any other question? Okay, if there are no questions, so we come to a stop here. The recorded video and its link will be uploaded to YouTube and also in your Moodle shortly. All right, so have a good weekend and good luck with your tests. All right, we'll see each other on Saturday because I'm sure I also have to invigilate. So we'll finally get to see it. Those people have been crying to see us. We'll meet physically in the tests. Okay, so have a good day. See you on Saturday.